Woohoo! Welcome back. Today we're going to be doing more integration by parts. Yay! And the rain still has not come, but I'm hoping it will soon. So maybe we can conjure up some rain with some very exciting and yet somewhat tricky integration by parts. And I'm going to start this one by saying sometimes it's not obvious you're making any headway. And you can already see ahead of time this integral where we've got the integral of e to the x sine of x dx. This is already going to be possibly a little bit difficult because I already told you e to the x doesn't get any simpler or more complicated. Derivatives, integrals, it stays e to the x. But sine also toggles between sine and cosine and plus and minus, but it doesn't get any simpler. So I already told you that this would probably not be a great candidate for integration by parts. But, and here's where Square Bear is always ready to just pounce on it and use integration by parts, because it turns out we can take advantage of the fact that this is going to toggle to do something really interesting. Okay. So let's go ahead and set this up. Pardon me. So to do this problem, you really can get away with setting it up either way. But I'm going to set it up this way. I'm going to go ahead and say, let's let u be sine of x. And then dv is going to be e to the x dx. Okay, so there's my u right there. And here's my dv right there. Okay, now if that's, pardon me, Square Bear, if that's my u, then my du, ooh, that looks like a v, sorry, is cosine of x dx, and my v is e to the x, right? Antiderivative, derivative, e to the x, it's always going to be e to the x. Okay, so let's go ahead and set this guy up. So I've got, I'll remind you, the integral of u dv equals uv minus the integral, and then remember we switch it up, v du. So the integral of e to the x sine of x dx is equal to, and then we're going to use these guys right here, the catty corner ones, the u and the v, e to the x sine of x minus, and then we use these two, the new ones, e to the x cosine of x dx. Okay, are you with me so far? So you can see what I was saying in the previous video, that in doing all of this, we haven't really changed the nature of this integral. But what we have done is we've introduced a minus sign. And the minus sign is going to be the key. That's going to be the thing that allows us to do this problem. It's pretty cool. So now I need to focus on this integral. So let me pull this over into the spotlight. And I've got the integral of e to the x cosine x dx. Now remember that there's a minus here. I'm going to leave the minus out for right now just to simplify things, but we'll have to put it back in with the minus attached. I'm going to follow exactly the same approach. My u is going to be the cosine x, and my dv is going to be the e to the x dx. Now remember that when you take the derivative of cosine, you get the opposite of sine. And e to the x, I mean, it's always e to the x. It's pretty cool. The graph of e to the x has slopes that are equal to the values of e to the x. Isn't that cool? It's kind of weird. It's kind of very cool. Okay, so then just this piece, remember, just this little piece. Sorry about that, Square Bear. I'm going to move you over. I know, you're right here. Yeah, you're just going to sneak over. You'll just be peeking in from the side. Okay, so then I've got e to the x cosine x dx is going to be, remember, it's the u times the v, so it's the ones that are slantways from each other. E to the x cosine of x minus, and then I bring these two together, and notice that there's another minus here. So that's going to actually make this a plus. Do you see that? So it's going to be e to the x times the opposite of sine x dx. Sorry about that, Square Bear. So that's e to the x cosine of x plus the integral of e to the x sine x dx. And this minus and that minus go together to make this plus, right? There we go. Okay, so take a look. Do you see where I got everything? Okay, so let's combine all of this together. Let me see if I can kind of scooch it so I've got some space and you can still see things. So I'm going to write down the original. Here, let me cover that. The original said the integral of e to the x sine of x dx is equal to e to the x sine of x minus this new integral e to the x cosine x dx. So far, so good? Okay. But then we calculated this integral. We did a second time through, and we got the fact that this new integral, this guy right there, is equal to this. Okay, so that means that I've got e to the x sine of x minus e to the x cosine of x minus the integral of e to the x sine x dx. Notice that that's equal to e to the x sine of x dx. Pardon me. This matches this. And I'm going to fold the equation on itself. Like literally, I'm going to fold the equation. I'm going to add e to the x sine x dx inside the integral to both sides. And that's one thing you should know about mathematicians. There is no limit to what we will do algebra with. We do algebra with integrals. We do algebra with numbers. I mean, we'll add things to both sides of an equation. Does not matter what they are. I mean, sometimes it doesn't work, but we'll always try. I've got two of these, so I write 2 times that equals, this cancels out, and I get e to the x sine of x minus e to the x cosine of x. What do you think? Now, I was very, very focused on what we were doing. And what I neglected to take consideration of is that in all this integration, if we're integrating and it is an indefinite integral, there could actually be a number over here, right? When you're integrating, there could be an integral, a number, because you take the derivative of a number and we'd never see it. So what I'm going to do now is I'm going to divide both sides by 2. So I get that the integral of e to the x sine of x dx equals 1/2 e to the x times sine minus cosine. And then I put in a big old C to take advantage, well, to compensate for the possible constant. And again, the way we've been doing this is I haven't been keeping track of the C's straight all the way through. We're just kind of sticking it on at the end. But you could be compensating and putting them into every step if you would like. It works just as well like this. Okay, we got that one. Woohoo, not too bad. Yay, you guys are awesome. What do you think, Square Bear? Square Bear's hungry? Square Bear is always hungry, but Square Bear is pretty happy about this. Okay, so, wow, we did that one. Are you guys ready for the dun 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 one? Okay, so you may want to pause. I'm going to keep saying these are not simple things, so you may want to pause. Give yourself a break, especially once you see what I'm about to do. Okay, so there's still time to pause the video if you would like. So you can pause and go practice and come back. Or you can stay here with us and keep watching. Up to you. Square Bear's here. He's got you. He's got your back. He's a little bit hungry, but he's always hungry. Okay. First off, we need to talk about what the heck that thing is. So hopefully you recognize tangent. And even if you did not take a trig class recently, hopefully you remember that tangent is sine over cosine. The -1 means that this is arctangent. Arctangent means that it is the inverse tangent. So it is whatever so instead of being tangent of an angle measurement, this is what the tangent was, and arctan of this gives us the angle. So it's kind of an interesting little creature. Now you'll probably have noticed we have not worked with this yet, and the reason we haven't is because it is not simple. It had to wait until now. In order to work with it, we're going to use integration by parts. However, I've got a little hint, and the hint is that the derivative of the arctan is 1 over 1 plus x squared. Now, hopefully you're looking at that and thinking, that's interesting. That kind of looks like some of the stuff that was going on with the trig functions and triangles, squares of things, and that's exactly what's going on. So if you want to see what the heck is going on here, let me know. But for this problem, I'm going to say, let us just take as given that the derivative of the arctangent is 1 over 1 plus x squared. Now, how are we going to use that? Okay, are you guys ready? We can totally do this. So I'm looking at this, and if I had no idea how to do this, I would say these are both pretty scary, but the arctan I'm really nervous about. And when I take the derivative of it, I get to x's, and that makes me really happy. X's are much more solid footing than arctangents, so that's what I'm going to do. I'm going to go ahead and I'm going to use this as my u. So my u is going to be this, and my dv is the only thing that's left now, right? If this is my u, then the only thing that's left is that little old dx. Okay. So, how do I take the derivative of arctan? Well, I told us how to do it. So I've got 1 over, pardon me, Square Bear, 1 plus x squared dx. And then here I have to take the antiderivative, so I come up to v, and that's going to be x. It turns out that even though this looks like a big mess, it's going to be great. It just takes a little bit of, this is a lot of faith. A lot of math is you're going to try something, And you're not going to give up even when your brain says this is too hard. Let's be an art major, because let me tell you, being an art major is not easy. So, or so I've been told. And so don't give up math. Just try it. And if it doesn't work, then we start over again. And I'm going to give you spoilers. This is totally going to work. So it's worth it. But we just got to be brave. Okay? Square Bear's here. Rawr. Square Bear will keep all the bad things from happening. One hopes. We need Square Bear right now. Okay. So the integral from 0 to 1. Now this is new. You notice what's going on? There are limits. Okay, I'm going to take a deep breath because we can totally do this. Okay, this is the UdV. And remember what we do is we go UV. So it's going to be X arctan X, right? Now, we can't just leave that there. We're going to do 0, 1, and then minus, and the integral from 0 to 1 of v du. So we're going to multiply these. So I'm going to have x all over 1 plus x squared dx. Now, at this point, my limits don't have to change because I'm still working with x. So that's the good news. The bad news is you may not know how to find arctan, which is, I understand that can be a little bit stressful, but let's talk about it. So let us do this part. So let me do this part, and let's expand it right here. I'm going to give myself lots of room. I'm going to plug in 1. So I've got 1 times arctangent of 1 minus 0 times arctangent of 0. And then minus this other integral. Okay. So the good news is this right here is 0. Right? 0 times anything, as long as it's defined, is 0. That's fine. What is the angle measurement that gives us a tangent of 1? So we want to know theta equals what if tangent of theta equals 1. So tangent means sine over cosine. That means sine and cosine are equal, right? When are sine and cosine equal? They're equal at pi over 4 or 45 degrees. Okay? You can also do that on your calculator. So this whole thing is going to be 1 times pi over 4. And the answer, since you were not asking it because I'm just recording this, but I'm imagining you're asking it, is how do we know whether we use radians or degrees? You almost always use radians. Unless someone specifically tells you, no, the fate of the universe is at risk unless you use degrees, you'll always use radians. Okay, go from 0 to 1. And now we've got, and this is what really intrigues me. I don't know if it intrigues you. What really intrigues me is that there's no more, this is not trig anymore. I mean, now that you've gone through this, you actually can see that there's trig in this. And in fact, in 2 sections, in 7.3, we're going to talk about why we might bring trig back into it in cases like this. But that's coming later. For right now, what we want to do is just find this value of this integral. So we've got pi over 4 minus whatever this thing is. So if I can find my paper, let's simply find this. And we don't have to worry about tangents or arctangents or anything. This becomes a brand new problem to solve. Okay, I personally see an x squared and an x. Whenever I see that, I get a u substitution. Now, I have issues with dead mathematicians that they set us up so that everything is u. So I'm going to suggest something, and you don't have to do it. You don't have to do it. If you'd like to do a u substitution, that's great. I'm going to use a w substitution, just because we have a u substitution up here, and there's a lot going on. So I'm going to do w now. So if I set the denominator equal to w, 1 plus x squared, what is dw? And we're doing exactly the same work. I mean, substitution and integration by parts are not that far apart. So dw is going to be 0 plus 2x dx. Okay, so in other words, if I have 1/2 dw, that's going to give me x dx. So my new integral is going to look like this. Now, I am a cheaty McCheaterson. Whenever I can, I'm going to cheat things because they annoy me or scare me or both. And whenever I'm doing a u substitution, or in this case a w substitution, sometimes I don't worry what the new limits are. I just put in some the a and the b, and then I decide what I want to do at the end. So these are just placeholders, a and b. I don't know what the new limits are. Now, could we go ahead and calculate the new limits? Absolutely. They're probably pretty easy. In fact, it would probably be 1 and 2, so we could deal with that. But I'm going to show you that you can do this, and then you don't have to worry about it. Okay, so I think I get 1 over w times, and then the x dx gives me 1/2 dw. That's going to give me 1/2 the integral from a to b of dw over w. Okay, so the integral of dw over w is going to be 1/2 times, what is dw over w? You got it, natural log of the absolute value of w gone from a to b. Okay, so now we get to make choices. Your choice is convert w back to x and use 0 to 1, right? Or 2, convert limits to w. You get to choose that. So if you want, up here, you can take w, and w equals 1 plus x squared, so you put 1 plus x squared in there. That's number 1. Or here, we had the limits from 0 to 1, and I switched them to a to b. So I can say in w land, 1 converts to w is 1 plus x squared, so that's going to be 1 plus 1 squared, so that's going to be 2. 0 is going to convert to 1 plus 0 squared, so that's 1. So, oh my goodness, all the paper. So, we have 1/2 natural log of w in the absolute value from, instead of being 0 to 1 like it was, and I switched to a to b because I didn't want to deal with it because I wasn't ready, and now I'm ready. Our new limits, instead of 0 is going to be 1, instead of 1 is going to be 2. So that's 1/2 the natural log of 2 minus the natural log of 1. Let me get that up there so you can see it. I know, this is a long one. Now, the last thing to remember, this is one of those problems where you have to remember all the math you've ever learned in your entire life. Do you guys remember what the natural log of 1 is? Natural log of 1 is what the exponent, so natural log of 1 asks e to what exponent equals 1? E to the 0 is 1. So natural log of 1 is 0. So it's funny because we started out, we're dealing with the inverse of tangent, and now we're dealing with the inverse of the exponential. Everything's the inverse. Everything is related. Now, unfortunately, natural log of 2 is just natural log of 2. It's not a nice number, so I don't have it memorized. Now, are we done? Should I circle this? And the answer is no. No. Hopefully, somewhere here, we know that this was this integral 0 to 1 of x all over 1 plus x squared dx, right? So the actual answer, the integral from 0 to 1 of arctangent of x dx is pi over 4 minus 1/2 natural log of 2. What do you guys think? Right, it's pi over 4 minus this, and this guy is that, and so, wow. You guys are amazing. You made it through that. I'm very impressed. So how did we do that again? Well, this one was the leap of faith. This one was knowing that the derivative of arctan was something nice. And so we took advantage of that to take the derivative to get ourselves out of trigonometry. Okay. Ooh. Now, there's one more thing I want to talk about. It's not a full problem, but I just want to introduce you to a concept. And the concept, dun dun dun. Here's Square Bear, because there are powers here. So there's something called a reduction formula. Sometimes the best you can do is just keep iterating the steps. And like I said, if I give you, sine to the 10th, x times sine to the 10th, or x to the 10th times sine, you just have to do it over and over and over again. The resulting equations are called reduction formulas because you can use them over and over to gradually reduce the exponents involved. And so I'm not going to prove this. I just want to show it to you. And I'm happy to prove it. Hopefully you guys can kind of see how this works. If you have the integral of natural log to the nth power dx, okay, then you're going to end up with, this is your u, right, is going to be natural log of x to the nth, and your dv is going to be x. Your du, right, is going to be, this is going to require the chain rule, n times natural log of x to the n minus 1 times the derivative of the inside, 1 over x dx. This is a lot. V, on the other hand, is just going to be the integral oh my goodness. Pterodactyl. Pterodactyl. Okay, do you guys see my mistake? Because I panicked there for a second. I was like, oh no, this is not going the way it should go. And we're almost 30 minutes and I don't want to redo the whole thing. Do you guys see the mistake? Okay, the mistake is right here. So let's take a look. If I'd followed my own advice, here's the u. And what's left for the dv? Only dx. So make sure you're, paying close attention. Sorry about that. So dv should be dx, not x. And then v, and those of you who saw it, nice work. V then should be x Now, what's great about this? Well, what happens, you can see there's my U right there. Oops, sorry, didn't mean to make marks on that. There's my U right there. There's my V right there. Now, what happens when I multiply these two? The cool thing is the X and the 1 over X cancel. And so all we have is this n, which remember is just a constant. It's 5 or 138 if somebody really doesn't like you. And then natural log of x to the n minus 1. So notice that we've got an equation that allows us to step down how bad this is. And we just have to keep using it. Use it over and over and over again until you get down to not needing it anymore. You get down to 1 or 0, depending on the setting. Okay? Woohoo. You guys are amazing. I am really impressed if you made it through. I hope you took some breaks. I am going to go and look and see if I can see the rain. Hopefully it's coming soon. And probably feed some cats because I don't know if you heard them, they're running around under my feet trying to get my attention. So I'm going to suggest that you go hug someone you love, or say hi to someone you like, or go out and stare at the sky, or stare at the moon, or go find something that fills you with love and hope and happiness. And, definitely get snacks, because that's always good to have snacks at those moments. And definitely hydrate, and know that I'm really, really proud of you. And I hope you have a great rest of whatever you've got going on right now, day, night, afternoon. You're awesome. So, math on and woohoo.